So plastic and cardboard. Coefficient of friction, plastic and cardboard. And there's usually a long list. Sometimes they'll have a single number, sometimes they'll give a range. Really, if you were designing something and needed to know, probably would run a quick experiment to know what's true for those two surfaces. So you can probably have a generally good idea just from looking at similar things. This is normal force. And this is friction. Or written in possibly English this time. Friction. All right, questions up to here before I change it around a little bit. All right, so I have a table right here. I'm going to push on it. So I'm pushing on it right now. What is the acceleration of the table? Yeah, to me it doesn't look like it's moving. So I'm applying a force to it, but it's not moving. The acceleration is 0. If the acceleration is 0, what does that mean?
You're not pushing on it up. You're not getting, there's too much friction.
All right, hoping not to get into that detail yet, but yes, hold that thought. In general, if acceleration is 0, what else is true?
Velocity.
Velocity.
It's not the velocity being 0.
It's constant. Velocity is constant.
Constant. Changing velocity is 0. In this case, the velocity happens to be 0, but ultimately, if acceleration is 0, all we know is that the velocity doesn't change. So, if acceleration is 0, then the change in velocity is 0, otherwise known as velocity is constant. Matter of fact, if that's true, the other one's true. If one's true, the other's true. There's one other thing. Connecting it back with what we were doing earlier. If acceleration is 0, that's done in silence. Said, this stuff is so awesome, how could I possibly contribute? You are just as awesome.
Force is 0.
More specifically, the total force.
Total force, net force.
Yeah. If acceleration is 0, the total force is 0. What is this state generally called? What's the one word that we use to describe this?
Equilibrium.
That's it. So all of these equilibrium. So as I pushed on this table, the acceleration was 0, it was in equilibrium. The big thing here is that the total force is 0. Now I'm applying a force to it. I can feel it in my leg. I know it's pushing on me, so I have to be pushing on it. So now we get back to what Yvette was saying earlier. Why is it not moving? What's making the net force 0? I'm obviously pushing on it.
Friction.
Okay. If I'm pushing on it, we'll just say with 5 newtons of force. What's the friction being applied?
-5.
Okay. If I increase my force, still not quite moving up, now say 10 newtons of force, how much is the friction?
Still 10.
You said still 10?
Well,
Okay, so but the friction is gonna match me.
matches, yeah.
It's gonna match it until I hit a breaking point. At some point, it will start to move. Then the question is, what happens to the friction? So my formula here is not necessarily gonna be an equal sign. It's because sometimes the friction is actually less than what you get when you multiply this stuff together. Because it's gonna match me up to a certain point. And because, and I think all of you definitely agree with this, everyone loves a graph. Let's take a look from a graph. At least no one's denying it. So if I'm looking at friction and I look at the applied force, friction is going to match, and then I hit a breaking point. And then what happens next depends upon the theory. The classic method, the one that the guy came up with several hundred years ago, and what most textbooks will have, is that it will drop and then go constant. This right here is the friction for when an object is moving, is actually sliding, and this right here is when it's not sliding until you hit that breaking point. Of course, we've got to have some vocabulary words to differentiate them. This is known as kinetic friction, kinetic dealing with movement. Kinetic friction, which we can write shorthand, F with a subscript K there. And over here, where it's less than, or where it matches, this is static friction. F with a subscript S. So I'm going to change my formula over here. This F equals mu y. If we're dealing with kinetic friction equals mu sub k times y. The coefficient of kinetic friction, or sometimes I'll say kinetic coefficient of friction, although I think the first way I said it was the proper way. In some places, we'll call it sliding friction instead of kinetic. Since the static friction is going to match until I hit that breaking point is what's determined that if you looked up the coefficient of static friction, it's the breaking point that is concerned right there. So this is the maximum static, Fs max. Or, because everybody loves an equation too, static friction is less than or equal to USY. So this is just to indicate that it's going to match until I hit my breaking point, and that's the breaking point. Questions to here?
What's,
Just make sure you said at static, it's not moving.
Right. It's not, the two objects are not sliding against each other. And let's be clear, that is, it's not moving relative to the object it's touching. It could be moving relative to something else.
so the Fs is less than and equal to, that's that little part between the P and the straight line?
That this point right here is U sub S times Y. That's your maximum.
Okay. So the in-between part is this?
This part right here?
Yeah.
That is, as soon as it starts to move, it quickly drops down to this.
Okay. But what's that in between? No.
It's a gap.
It's a gap,
It's the same
okay.
point on the graph.
The
It's a gap.
friction, I've never seen enough detail to actually talk about that transition.
Okay.
If it's moving, it's here. If it's not moving, it's somewhere up here.
Okay.
And it magically just goes from one to the other.
So
Or
why
not.
wouldn't the line just start at the P?
Oh, wouldn't that start up here?
Yeah.
All right, hold that thought.
Okay.
Now, this is the classic friction applied force plot that almost every textbook uses. However, there's been some research into saying this is not quite right. Because if you look up a table of coefficients of friction, they claim that there are large error bars. Yeah, I might say the coefficient of friction is 0.2, but that actually could be 0.1 to 0.3. But it's often not written, the whole thing's not written out of properly, it would give the average value with a standard deviation to give you some idea of how spread out it is. The other group says there really is no difference between US and UK. The only difference is our imagination, but if you actually did an experiment, they are so close to each other that there is no difference. And they claim that my graph for applied force looks like the following. You go up, it matches, it matches, it matches, till you hit that breaking point, and then it just levels off. So it seems like it'd be very easy to do an experiment just to see which one of these works, which one of these is true. And I cannot find it if they've done it. I found a college senior paper in which he did this, and he did not run enough trials in order really to come up with anything solid. But I haven't found, I just haven't found it yet. Presumably it says somewhere, because why else would these people suddenly go, hey, the way the books have been saying it for a couple hundred years is wrong, or not quite right. So if this is the case, then friction is less than or equal to this mu y. I bring this up just in case who runs across it. It's possible that when your kids start taking physics, that this will be the primary one and the other one won't be. It takes a while for things to change. There was an experiment done in the 1890s to show that in space there was no ether. And what I mean by that is they knew waves needed something to travel through. If you have a rope and you move it up and down, you can see waves ripple back and forth. It needs the rope. Sound needs air. In space, no one can hear you scream. Unless, of course, you have a walkie-talkie, then you can. The idea was that if waves need to move through something, then how does sunlight, which travels in waves, get to the Earth? And they said, well, there must be something that's traveling through. So they came up with this idea of ether, not the gas that we know of, but ether as an ethereal. 1890s is generally there was an experiment done, which is generally the one pointed to say, hey, this is the experiment that shows us that ether doesn't exist. I have a textbook from the 1950s that still refers to ether waves. So it takes a while for changes to happen in textbooks. I first saw this in the 90s, so we are now probably 30 years later. I'm still seeing that mostly over there. But at some point it might change.
I'm just confused why it would drop.
All right, so here's the way I think about it. If I have two objects that are pressed into each other, so looking at sort of the microscopic, if I zoomed in really far, I have these two pieces like this, like badly interlocking pieces. And in order to get it to move, I need to somehow either break some of that off or get it to pop out so that it can move. Once you pop it out, it's not wedged in as far, and so therefore it slides more easily. That's the way that I think about it. The trouble is, in terms of how come they don't know, or why don't they have anything better than what they came up with hundreds of years ago, is that engineers, as a general rule, are the ones who deal with friction. And they are a very practical group, and they have something that works. Physicists, the ones who'd be more apt to go, wait a second, is that right? Tend not to deal with friction. Personally, I dealt with subatomic particles. Friction doesn't exist at that level. You're dealing with tiny particles hitting tiny particles. So there's a group at NC State looking at this, but I don't know what progress they've made since I heard a talk back in the 90s. Questions before we throw friction into the problem? Then let's throw friction into the problem. So what I'm going to do is we're going to keep all this the same, except this time I'm going to add another piece of information. U sub s is equal to 0.6 mu sub k is equal to 0.5. As a general rule, use of K is going to be less than use of S. Theoretically, there's no limit to what US could be, but I've seen only one material where the coefficient was more than 1. Seen as in a book or on the screen, but not actually seen in person. It is always a positive number, despite results of some labs I've seen. All right, so we have friction involved now, so let's throw the friction into it. Sorry, friction. First off, is it going to move? Well, probably not, actually. So my weight we established was 49 newtons. The normal force has to be 49 newtons to balance it out. So what is my maximum static friction? So, take my coefficient times the normal force. My maximum static, 0.6 times 49. Is that 29 point something? What is it?
29.4.
9.4. Am I going to overcome the static friction? Because what am I pushing with?
3 newtons.
Yeah, that's nowhere near close enough. So the question is, how can I get this thing to move? Okay, that's one way. What's another way, realistically, to get something to move that's sort of stuck like that?
Applying a force a different way.
Okay, without applying more force, suppose 3 newtons is all I can muster. Well, sure, some of you have done this before, not necessarily thinking what you're doing. But that didn't come out right. You knew what you were doing, you weren't thinking about what was happening sort of at the physics level.
Change the friction, the kind of friction there is.
And how can you do that?
Like when you move big furniture across hardwood floor, you put a blanket under it.
So that's one way of doing it.
Slides more easily.
So you can change the surfaces. One way is to put something underneath it, and another way, what I was thinking of was add a lubricant. So we'll spray some WD-40 in there, and what that's going to do is it's going to drop this. So let's say it drops it to 0.06 and 0.05. So now that I've dropped it by adding a lubricant, this is 0.06 and this is 2.94 newtons. Therefore, will it move now?
Yes.
And because it will move, we are dealing, yeah, but all we need to do is get it to move. Because it does move, it is now kinetic. And so we now use the actual, so it moves, so the kinetic friction is 0.5 times, 0.05 times 49, which is 2.45. That feels somewhat right. You did not get 2.45?
0.04.
0.05 times 49.
Yeah.
That's good, okay. So now the force is acting on this thing. I've got 3 newtons going to the right. I got 2.45 newtons trying to stop it unsuccessfully because we are that mighty. So now my net force. I have 3 going to the right, 3 I hat, minus 2.45 I hat. And we get 0.5 5 newtons I hat. That's my total force acting on this thing. And I can find the acceleration by plugging in F equals ma. So that 0.55 is equal to 3 times A. Whatever that is. 0.18 repeating
That's correct.
meters per second squared. I hat. Now, unfortunately, we could then, in physics, you could do Box-on-Ramp, in which case you then have to figure out what the normal force is. Unfortunately, since this is not a trig-based course, we really can't get into very complicated problems. I'm sorry. If you want more complicated problems, I'd be glad to, if you all want it, glad to go do more complicated. But that's probably as complicated as we're gonna get.
So we're always gonna have to start off with doing the friction static max first to determine if we can do the friction kinetic, or the kinetic friction.
Unless I state in the problem that it's all, assume it's gonna move. But yes, in general, you would start out with, is it even gonna move?
Right.
If it is gonna move, great. If it's not gonna move, then, well, the acceleration is 0.
Where did you get the 0.55 from?
So I had 3 newtons going to the right. The friction was 2.45 newtons going back that way.
Oh.
And so the total. Just to give you some sense, rubber on asphalt, so, if a car skids, I think that's somewhere around 0.7 for coefficient of kinetic friction. For the stuff that we do in lab, it's usually somewhere around 0.2, 0.3. Occasional negative, occasional something huge. I will see you tomorrow.
You know, we get up.
Pardon?